Okay, welcome back everybody, and today we will be continuing doing parametric equations. So let's just review a little bit. Before we have y equals 2x as a function, but now we say, hey, there's another way we can do it. That is, we can transfer it into x as a function of t and y as a function of t. So through the relation between x and the t and y and t, we can actually establish the relationship which is hidden inside these two relationships. Okay, we talked about how to transfer between these two kind of forms, and then we also say the intuition is basically you have a motion going like that, and for every moment you can decompose the motion into a horizontal one and a vertical one, and each one is changing with respect to the same time t. So x of t and y of t. Today what we want to do is we want to extend what we had before for calculus for something like f prime x and the integral of fx dx. We want to extend those kind of ideas to a parametric equation, x equal ft and y equals gt. And we can see some tricks we can do to calculate the same thing, which is actually very straightforward. And then we will try to see some advantages of using parametric equations. Okay, so that's what we need. So we will be focusing on two things for calculus. First, derivative. Second, integral. And for integral, we focus on several applications. The area under the curve, the volume by revolution, and then the arc length, and surface area. So these four things are the applications of integrals, but we can see they are basically roughly the same idea. Okay? So let's first talk about the derivative. Okay. Let's talk about, for example, some example like this. X equals, okay, cosine t, and y equals sine t. Okay. As far as we know from this, it represents a circle. In this case, it's a unit circle because we don't have centers here, which are 0 and 0, so it's centered at the origin, and r here, which we basically pick to be 1 for simplicity. Okay, so we want to know the derivatives, for example, at here, and find the slope of the tangent line. We want to know the derivative of the here to find the slope of the tangent line, which from the old trick is nothing but dy over dx. So we will start from this formula and work towards what is dy and dx if I give you any kind of point. By the way, the t here represents the angle here. Okay, so let's talk about it. Let me redraw the thing to make it more clear. Okay, the t basically represents the angle here you have. Okay, so, well, how do you take the derivative? Technically, you do know how to take the derivative of cosine t, right? That is nothing but negative sine t. This is what you know on how to take the derivative. But just to be careful, when you say take derivative, you need to tell people you are taking the derivative of what with respect to which variable. In this case, your x is a function of t. So yes, you can take the derivative to be negative sine t, but what you really have is dx over dt, which is the derivative, the changing rate of x, as t change a little bit, and that is given by negative sine t. Similarly, from the formula, your y, if you take the derivative with respect to t, which equals cosine t. So far, so good. It's very easy. It's just you are using some other variables other than dx and dy, but it's hidden here. Okay? Now, let's think about number one, how to think about this thing. What do you mean by dx over dt? Okay. Last time we were saying if you have a motion, for example, like a rotation like this, at any time you have an x, you have a y, and that is your horizontal and the vertical. Okay, trajectory. Now if you take the horizontal trajectory with respect to t, that will actually give you the horizontal velocity, which tells you how fast the horizontal trajectory is changing. That is the horizontal velocity. You take the derivative with respect to t again, you will get the acceleration, but only for horizontal. Okay, so that is saying, as the whole thing is moving in this way with a certain speed, your x, if you think about it, is actually moving from here all the way to here. And then this thing go all the way to here, and then you move all the way back. And you have a certain changing rate, but only works for your x coordinate. Similarly, as this point go from here to here, your y is going to go from here all the way up. and then all the way down, and all the way up. And the whole motion is actually a combination of the vertical and the horizontal. So each one separately is going to tell you the horizontal velocity and the vertical velocity. Okay, that's how I think about things like this. Okay, so now if you think about another one, which is the first motion we introduced, we just throw something at this height. The trajectory looks like this, right? Okay, so what's your horizontal velocity? Well, it's always 2 meters per second. It's always there, so that's your dx over dt. Constant speed. That is why your trajectory is 2t, which is the integration of this. What is the vertical velocity? That is actually the acceleration times t. Your vertical velocity is actually going faster and faster and faster. That should equal to your dy over dt. That's your y. Your y equals 1/2 gt squared. Actually, there is a minus. Okay, and plus the initial position. So that's how we do it. So this is the horizontal velocity and the vertical velocity. That is very good. But now let's go back to the traditional thing. We have this. We have this. To find the slope of the tangent line at a certain point, what you really need is dy over dx. So can you think about a way to get dy over dx from dx over dt and dy over dt? That's the question. Okay. Now, doing some trick, I think you can see it. Dx over dt and dy over dt equals dy over dt divided by dx over dt. Now note, by simple algebra, that is dy over dt. Divide means times the reciprocal of dt over dx, coming from dx over dt. And from here you can see magically these two dt just cancel each other, and you have dy over dx. Okay? So from now on, every time you're talking about those kind of ratios, you can simply do the calculation using elementary algebra. And let me explain why you can do this. dy over dt tells you if t changes a little bit, it times dy over dt, it's going to tell you how much your y is going to change. This is actually the changing rate of y with respect to over dt. For example, if dy over dt equals 3, that means your t changed by 0.1, your y is going to change by 0.3. That's triple the size. Similarly, if your dt changes a little bit, your dx is going to change. That ratio is given by dx over dt. For example, if dx over dt is 2, that means this one is twice the size of dt. Okay? If dy over dt, let's use 4, equals 4, that means dy is actually 4 times the change of dt. So if dt changes for 1, this changes for 4, this changes for 2. Great. Now your question becomes, if x, what is dy over dx, right? dy over dx is basically telling you the ratio, if x changes a little bit, how much y is going to change, and what's the multiplier. From here you can see, with the example we have here, if your x changes by 1, and x is twice the change of dt, so dt is going to change by a 0.5 in order for x to change by 1. But now you know the dy over dt, which means the change in dy is 4 times the change in dt. So if x changes in 1, your t is going to change in 0.5, half the size, but then you times that by 4, your y is going to change by 2. So if x changes by 1, your y is going to change by 2. And where did that ratio come from? That's basically the ratio of here over the ratio of here. Okay, so that's the ratio of the two changing rate with respect to t. So one way or the other, you can understand things in this way, or you can simply forget about it and just say, well, if I see dt and dt, they cancel each other. Okay. So that's basically how we are going to do this for derivatives. Okay, before you have y equals x to x, you can take the derivative directly. Now you have x and y to be a function of t. What you need to do is you can simply just take the derivative of x with respect to t, you take the derivative of y with respect to t, and then you just take the dy over dt divided by dx over dt. That gives you the same thing. We will see some example right away, formal example, but I just want to show you that in the notes, we basically write this idea here, and the most important thing is this definition here. That is how we are going to calculate the derivatives at any moment. Let's take several examples. First one, find the, let's just say dy over dx of x equals 2 plus 3t and y equals 1 minus 4t. Okay, solution. As far as we know, this is actually a straight line passing the point 2, 1. Okay, with slope. Try to recall, it's negative 4 over 3, which is negative 4/3. So if I'm looking for dy over dx, I should have a constant, which is just this one. Now let's verify if our method works. Okay. Now, what is dx over dt? That is how fast is my x changing. That is going to be dx over dt, which is 2 plus 3t prime. That gives you 3. What is dy over dt? That is going to be the derivative of this, and you can see it's nothing but 0 minus 4. Okay, then dy over dx equals dy over dt divided by dx over dt, dt cancel, which is nothing but negative 4 coming from here, dy over dt, divided by 3 coming from here. Okay, that is exactly the slope, so for this case it worked. That's great. Let's try something else. Let's try this. Find the formula of the tangent line of x equals cosine t, y equals sine t at t equals pi over 4. Okay, from what we have here, we kind of know this is going to be a unit circle. Pi over 4 is here. So we know at this point, your tangent line is going to be exactly going down for 45 degrees. The answer should be negative 1 in terms of dy over dx. Okay, and then we can actually go ahead and try to find the slope, the straight line. So if that's what we're looking for, we need 2 points. We need a point, and we need a slope. All right. Let me make it more carefully. So number 1, let's talk about point. This point happens at t equals pi over 4. And remember, your point is your xy value. Your xy is given by the formula. So x equals cosine pi over 4. And y equals sine pi over 4, given the parametric formula. And they both equal to this. So the point is given by this. From our experiences, this definitely works. Okay, that's 45 degrees. Now for slope, we're looking for dy over dx. Okay, according to what we have, it's going to be dy over dt over dx over dt. And dy over dt is nothing but the derivative of sine. That gives you cosine t divided by negative sine t, which give you negative cotangent. Let's just keep things in this way. Okay. From here you can see dy over dx, because you get it from dy over dt and dx over dt. Your final function will be in terms of t. Okay, but that's no big deal. As long as it's just before you plug in x, now you just plug in t. And you can plug in t equal to pi over 4. That tells you dy over dx at this moment is going to be cosine pi over 4 negative sine pi over 4, which give you negative 1. Which equals negative square root of 2 over 2, square root of 2 over 2, which is negative 1. Okay, so you know the point, you know the slope. Now you can easily write down the tangent line. Whatever form you prefer. Okay, I would just go with point slope form. Feel free to simplify if you want. Okay, So that's the solution for this one. From here, you can see it's actually not hard. You basically take the derivative as you did before, but this time you do it with t. And because you have two formulas, you take it for twice, but when you finish, you just divide the corresponding ones. So dy over dx, if you think in another way, that is nothing but, what do you mean by dy over dx? That means at this moment, if I move to here, my x is going to change, my y is going to change, okay? And what is the ratio of this over that? So it's very fair for me to just take the changing rate of x, or y, divided by changing rate of x, which give you the same thing. So that's exactly the same definition. That is good. Another interesting thing about parametric is this. We just finished, right? This is dy over dx. Moreover, this is actually dy, and this is actually dx over dt. Now let's investigate what happens at t equals 0. At t equals 0, our dy over dt is going to be cosine 0, which is 1, and our dx over dt is going to be negative sine 0, which gives you 0. From here, you can see dy over dx is undefined, because you're basically dividing by 0. All right, this one's on the bottom. The one on the bottom is undefined. Does it make sense? Well, if you think about the circle, t equals 0, basically asking you what's the slope of the tangent line here. Technically, it's infinity, right? So it's divided by 0, you got infinity. Of course, it's undefined. That is good. So before you would say no derivative here. Or you can say no changing rate. Okay? But now, if you look at the horizontal and the vertical separately, you know your answer is not complete. Actually, there is a changing rate. Okay? There's no changing rate in x. At this moment, you're not moving left or right. But at this moment, you are moving up. Correct? If you're thinking about things are going counterclockwise, you are moving up. And you're moving up at exactly the velocity of 1. Okay? So before, you would think there is no derivative here, therefore there is no changing rate. And that is because you are dividing by 0. But now you should tell yourself, okay, there is a changing rate. The horizontal changing rate is 0 here, but the vertical changing rate is still there. However, the ratio between the vertical divided by the horizontal is definitely going to be undefined. So there's no ratio between them. But it doesn't mean we don't have a changing rate, because technically for this motion, this one is still changing. From here, you can see that y and x restriction. If you start to think about fx, your changing rate can only go horizontally. There's no vertical thing. Okay? So that's why parametric, again, has been proven to be more flexible. We can try some other examples, but I really think this is easy. So if you think about it, like we can have x equal to cosine squared t, and y equals square root of t cubed plus 1. And really, I don't even know what the graph of these two looks like, but if you want dy over dx for a tangent line, you simply just take the derivative of the first one. Okay, which is nothing but a single function. And then take the derivative of the second one with respect to t. And then take this one divided by this one. So you got the derivative. You plug in the t, you can have the horizontal, you can have the vertical velocity. And moreover, if one of them is 0, you are dividing by 0, which gives you no changing rate. But technically, you still have changing rate. It's just one of the changing rate is 0. So it's not moving horizontally. Okay? That is very good. And that's it. That's everything you need to know about taking the derivatives. Okay? So now, one more thing, which looks a little bit confusing at first. And let's continue with this example 2. Let's say 2, continued. We still have x equals cosine t. And y equals sine t, the same thing. And we already know dx over dt equals negative sine t. And dy over dt equals cosine t. We already know that. Now my question is, find the second derivative. Okay, this means the second derivative of the parametric equation. Why do I want to do that? Maybe I want to just check the concavity. Is it concaving down? Is it concaving up? Do I have a local maximum or minimum? So I do have all kinds of reasons why I want a higher order of derivative. But now the problem is, starting from here, and here, how do you take the derivative again? Let's think about it. Okay, you can certainly take the second derivative of this, but then you realize I'm just taking the derivative again with t, not with respect to x. Right? Similarly, I can take the derivative of this one again, but again, I'm taking the derivative of respect to t, t, not with respect to x. And then if I use this one to divide by that one, I'm going to have the second derivative of y divided by the second derivative of x, which is not what we want here. Okay. So how can we take the d tool and try to make this work? That is a question. Okay, maybe my screen froze, so I'm going to need to restart this. Okay, let's take a moment. Okay, so it's still working. Yeah, let's go back and say this again. So I basically have dx over dt and dy over dt already calculated. I want to know the second derivative of this, right? And we found it's just take the derivative of these two with respect to t for the second time, it doesn't work. But now let's take a d tool. Okay, let's think carefully what we mean by this. Okay. This means I already have dy over dx, and I want to take the derivative of that thing with respect to x again. All right, let's take these two, keep this. What is dy over dx? Well, technically it's this over that, so we finish that thing. That is going to be this. Now this time I want to use negative cotangent. Now, see what we have. We want the derivative of this with respect to x. But we don't know how to do it. We do know how to take the derivative of this with respect to t. So let's think about it, okay? This over t. Okay, what is the derivative of cotangent again? If you don't remember, what is the derivative of tangent x? It's going to be secant square x. So derivative of cotangent is going to be negative cosecant t with a square, and the negative cancel with this. Good so far? Okay. That is the derivative of this with respect to t, but you do want this one to be x. Part of it is already done. You do want an x. So how do you change this dt to be dx? From here, can you see that? You simply just times a dt here. Then they cancel. You do have this one. Okay, so let me wrap things up. Here's a function of t. Okay. You want the derivative with respect to dx. It's nothing but the derivative of this one with respect to t first, and then times dt over dx. Now you can go ahead and try to do this. Okay, no problem. But what is this? Well, that's dt over dx. Do you know dt over dx? The answer is no. But think again. Do you know dx over dt? That is actually the derivative we just did. That's negative sine t. So if you times this, it's actually the same as dividing. It's dividing dx over dt. And we know dx over dt is nothing but what we did before, that is negative sine t. Up to here, we find the second derivative. Okay, negative cosecant cube t. And now if you want to know the second derivative at which location, just plug in t. Okay, So it's done. Now let me wrap things up. Okay, here the thing we just did. dy over dx. We can use dy over dt divided by dx over dt. When you finish, you should have some function with respect to t. Okay? Now you want to take the derivative again with respect to x. You just take the derivative again, but then you realize, wait a second, I'm taking the derivative with respect to a variable, but my function is giving you another variable. I don't know how to do that. I only know how to take the derivative with respect to the variable we have in the function, which is f prime t, which we just did. But to change it to another ratio or another differential, all you need to do is just times a ratio to make sure these two cancel and the one you want remain. But whenever you time something like that, that will involve two ratios of two variables. And all you need to do is just find a way to find this ratio. And usually it comes from the derivative. In this case, it comes from dx over dt. Kind of makes sense here? So this is actually an extension of chain rule. If you have a function of u, but you do want to take it with respect to a derivative of t, meanwhile, you know u and t has a relationship. Then what you do is you just take the derivative with respect to u first, but times a derivative of u with respect to t. That's exactly the trick we did before. Okay, so this comes from chain rule. At first, it seems like it's random. It's like you just make up a ratio and cancel things, and suddenly things are just what you want. But keep in mind, whenever we write down ratio of this, like this, dy over dx, or du over dt, actually we can calculate it because we know how to calculate the derivative. That's exactly what derivative is for. When x is changing a little bit, what's the ratio of change ratio of dy? When t changes a little bit, what's the Okay, so that is basically how we take the derivative. It's fairly easy, but I strongly suggest everybody to try the second derivative for once or twice, or even you can push yourself to be the third derivative, which should be the same idea. Okay, and make sure you understand what's going on here. Basically, even though you're trying to play with chain rule, but really, seeing the format, you're just playing with algebra. Okay, which is like, I have a fraction which will cancel one of the variables, give me another variable. So after a while, you can basically forget about this because when things get complicated, it's really hard to think about it, but it's really easy to trust your algebra. Finally, for derivatives, there is one more thing. That is from physics. Let's say you have some motion, you have some velocity. At the moment, okay, the horizontal velocity, it can be decomposed into horizontal velocity, which is, for example, 3, and you can decompose that thing into a vertical velocity, which is 4. Then automatically you know the speed should be the horizontal combined with the vertical, right? That will give you this. So because they are both vectors, you should actually obey a vector summation, which give you a right triangle. So that is given by Pythagorean Theorem. For this thing, we define it to be the speed, which is how fast the object is traveling. Okay, so it should be a number. It should not have any directions, right? I'm traveling at 20 miles per hour, no matter it's to the north, to the left, to the bottom, or to the right, okay, or southeast, whatever. And meanwhile, it should combine the vertical and horizontal velocity. And from here you can see it's very easy. It's going to be a Pythagorean theorem. Okay, the horizontal velocity plus the vertical velocity, and for horizontal velocity you just have dx over dt, that's your horizontal, plus dy over dt square. That is going to be your speed. Okay, I put it into the formula here, very easy to understand. I put a double bar here to indicate it's actually the magnitude of the total velocity. Okay, to see an example, very easy to see. Consider the rotation, right? We did dx over dt equals dy over dt equals, let's make it again, okay, negative sine t cosine t. So what is the speed? As this one move from here to here. You can see as this one move from here to here, your x is going to have a velocity, which is changing. It's actually slower here, it's fastest here, and it's slower here. Okay, so it's almost like Shoo. Like that. That's the best I can do. Okay, it's basically all oscillation, like a spring system. Okay, oscillation. So it's fastest here, it's slowest here. Okay, but now if you think about the speed, which is nothing but square root of this one square plus this one square by the formula, that gives you sine square t plus cosine square t equals 1. That means even though your horizontal velocity is changing with respect to time, your vertical velocity is changing with respect to time, but the total velocity, which is pointing this way at any moment, which is tangent to what's going on here, okay, is a constant speed as your angle is changing with a constant speed, which is your t. That kind of makes sense, right? If you change the angle, you just take this one with a uniform angular speed, then the linear speed will be a constant too. Okay, that is actually reflecting on this speed formula. Okay, so that's what we got. Cool. Now the second thing is basically doing the integral. There are multiple formulas here, but I just want to emphasize several examples. Okay, because basically the idea to do it are roughly the same. We will take it with some interesting examples. Let's try first a easy example with respect to circle. So we want something we know. Find the area of the half circle. To make things simpler, okay? Half unit circle. Top half unit circle. Which is this. Now remember, we all know how to do this. Okay. But it's given by the formula, this time a parametric. Cosine t, y equals sine t. And make sure if you are only talking about the top, what you technically need to do is, okay, your t can only go from 0 to pi. Okay, we're trying to find the area under this curve. Our question is, how do you do integrals in terms of parametric equations? And this is what we do. Okay, number one, we set it up using the traditional integral with dx. So this is clearly from -1 to 1. Okay, and then if you think about what we're trying to do here for all the areas, we simply put fx here. Okay, but when you say fx, you are technically mean y. That is by traditional solving the derivative. Okay, oh no, solving the area under a curve. Fx, we replace it by y. But now, what we do is we want to change everything here to be in terms of t using the formula here. Okay, let's see. Number one, y is really easy. Y is going to be sine t. That's coming from the formula here. Okay, now here is dx, and you want to change it to be dt. Okay, and how do you do that again? If you think about it, we do know x equals cosine t. Now, this is actually like a u-sub. Dx is going to be negative sine t dt. Now, which one do you want to put here? I want this side to replace this side. So what you do is you simply just put everything here to be d cosine t. That is your x, right? And then when you finish, this is nothing but sine t. D cosine t, that gives you negative sine t. Moreover, it gives you dt. So we start from here. We see a y, we change it to be x, to be the formula with t. We see a x, we change it to be a formula of t. We see if any of them come with a d, you just simply take the derivative and attach dt. So far, we have successfully transferred everything with y and x into t. Then perhaps we should also change the ending point too. For this case, it's really not hard. You can do the math yourself. It's coming from pi to 0. Pi corresponding to -1, and the 0 corresponding to y. 1. To think about it, let's just say your x is cosine t, right? Your x go from -1 to 1. Then when x is -1, your t is pi. When x is 1, your t is 0. So that's how we find this. Keep in mind, these -1 to 1 are corresponding to x value, and your x is cosine t. Okay, let's switch so we don't have to deal with negative. Okay, you can do this by yourself. This easily give you pi over 2. Okay, note, use half-angle formula. Okay, as we proceed further into later chapters, you can see we quote chapter 7 again. But from here, you can see there's nothing tricky. So the key is set up everything in normal sense. Y, x, whenever you need. And when you finish, just replace all the x and y by your parametric equation. Of course, this is something we know before. It's rather easy. Now, let's do this. Let's find the area under the cycloid This is something you cannot do before. Remember, you cannot even define cycloid in a nice way before. Okay, for one complete. Cycle. I need to give you the formula. Do you still remember the formula? It's r theta minus sine theta. We simply take r equals 1 in this case, okay, to make your life easier. And a y equals 1 minus cosine theta. This is a cycloid for one complete cycle. So let's just say 0 less or equal than theta less or equal than 2 pi. Let's try to do that. What is it? Well, let's draw a graph. Remember that thing just go from here to here, and then that thing start to actually do the same thing again and keep going. That's the cycloid, and we just care about what happens during this. Okay, this is something cannot done in traditional method because simply you don't know how to do it. Okay, you don't even know what's the formula of this graph, but now you certainly can. So let's set up. This is 0. Here it's going to be 2 pi r, because that equals, this whole thing here equals the circumference of the circle. But if you don't remember it, that's also fine. This is just x0, and this is x1. And you know this one corresponds to theta is equal to 0, and this corresponds to theta equals 2 pi. We are going to change everything in terms of theta either way. So you can probably just say, hey, I named them to be x0 and x1. Later, I just change them to theta. So x0, x1. All right? Again, fx dx. I don't even know what x0 and x1 are. Now, fx is nothing but y. Complete. Now, replace your y with the real formula with theta. That's your y. Replace your x to be this. That is theta minus sine theta. Okay. Now, since everything is in terms of theta, you better change your ending point. Okay, from x0, x1 to from 0 to 2 pi. You don't even know what x0 and x1 are, but you really don't care because you know the starting should be when theta equals to 0, and the ending should be when theta equals 2 pi again. So that's the setup. Okay. Now to finish. Nothing to do here. Okay. Here you have a d. That basically means you need to take the derivative, which is 1 minus cosine theta with respect to theta. So you need to times the d theta here. Okay, the whole d whatever equals this and d theta. That is just the way how differential rule works coming from chain rule. After that, what you have is from 0 to 2 pi, 1 minus cosine theta square. I'm just going to skip the calculation. You can do it by yourself. The answer is going to be, 3 pi r cubed. Oh, there's no r, so 3 pi. Here, again, finish by yourself. This is easy, this is easy. Half angle formula for the last one. Sounds good? Okay, so that's how we do this. We basically set up everything in the old way, just replace an x and y to be the parametric equation, and then we got how to do the same thing in the new variable. Okay. Now maybe you start to wonder what is volume, right? Volume by revolution. We can do an example actually here. Okay. Find the volume of a unit sphere. I'm taking all the simple example. Not actually these are not simple, but some common example here, like a circle, like a sphere, to just show you that this works, because you can verify that. You go ahead and try to find more examples, you had done before. But let's say, what's the volume? Well, the volume is basically this part rotated with respect to x by the x-axis. Okay, that's the first way of doing it. Then what we can do is we can simply use the washer method. The volume is nothing but going from -1 to 1, okay, pi r squared dx, where your r is technically just your y squared. Okay, every time you're doing what you're doing is basically rotating this one. For a complete cycle, you receive, I better not draw it, this is really ugly. Okay, you receive a disk, and they add all these disks together. So from -1 to 1 dx, okay, pi r squared, your r, however, is just going to be your y in this case. Done. Now, let's change it. Let's change it to be pi, your y. Remember, by parametric equation, it's sine t squared. Your x is nothing but cosine t. Now, your x, as we did before, go from pi to 0. That's it. This is how you set it up. And to transfer it, it's really easy. You're just plugging x and y. To finish, it's nothing but pi 0 sine square t negative sine t dt, which is from 0 to pi sine cube t dt. There is a cube here. There's a negative sign here. And I switched the starting and ending point so they cancel. This is basically what we have for the volume of a sphere. Finish, you should have 4 over 3 pi. Okay, pi r squared. Oh, so, sorry, 4/3 pi r cube, but your r is 1. Okay, finish by yourself. The thing you probably need is you need to change this one to be sine t 1 minus cosine squared t. You take a sine square out, and then from here you distribute the sine t, you will be able to do it. Okay, so finish by yourself. That's the first way. Second way. This way is interesting. Remember, in Calculus 1, you also learned something called a cylindrical shell. I don't know how you guys think about it. I always think about it in terms of like a toilet paper. And the formula is given by, if you have something like that, you rotate it. Like this. You basically got a shell, which is a cylinder. Now you add all this kind of shell together. I won't go into the details, but you can do it yourself. It goes from 0 to 1, dx. The formula is given by 2 pi rh, where r is the radius of the cylinder. So in this case, r is x, and your h is going to be how tall this is, which is nothing but 2y. So if you just set things up using cylindrical shell, this is what you get. But again, we can change this. We can change it to be 4 pi. Your x is nothing but sine t. Your y is nothing but cosine t. And your dx is nothing but d sine t. Now everything is in terms of t if you're talking about parametric. The only thing you need to figure out is how do you assign the starting and ending point of t. Remember, this time your t go from pi over 2 all the way to 0, because you're starting from 0. Okay. Spend some time and figure out why this is happening. But then what you have is 4 pi over 2, 0, sine t, cosine t, and another cosine t from here, which is cosine squared t, dt. I think this one is easy, so we can just finish it really quickly. 1/3 negative cosine cube t. Okay, plug in pi over 2, plug in 0. Okay, plug in pi over 2, you got nothing, because cosine pi over 2 is 0. Plug in 0, you got cosine 0, which is 1. So you got 4 pi over 3. So this method also works. That's it. Okay, hopefully I already showed you enough examples. Basically, for volume and area under a curve, you just set up things in terms of x and y. And if you have trouble with this, you should go and review calculus 1 instead of, being mad about yourself on parametrics. There's nothing about parametric here. But once you finish, just make sure you change x and y to be your parametric equation, and make sure you match up the starting and ending points. Using this new variable, the rest is actually straightforward. Okay. Sounds good? One thing I didn't mention here, that is, consider how we did the area of the circle here, right? What we do is we do from -1 to 1 square root of 1 minus x squared dx. Now I'm going to ask you this question. If it were you to solve this equation, what are you going to do? Probably the first thing you're going to do is you're going to assign x equal to cosine t. You'd call this a trig sub. And this one become, okay, pi to 0 square root of 1 minus cosine squared t dx, which is negative sine t. And you finish this thing, right? And dt, whatever. Did you just realize you call it a trig sub, but what you really did is you changed your formula of the circle to be a parametric formula. So actually everything we had in trig sub is nothing but to represent the original graph into another parametric way. Actually, if you think about for any u sub, for any substitution we did before, it's simply change a variable. For example, you take a u equals x squared. What do you mean by that? That is basically, okay, my x equals square root of u. I got a new variable, okay, parametric variable to rewrite my old function. So actually, we are doing parametric all the time. You just didn't realize it. You think it as a trick, but really what you did is parametric equation. Okay, it's a change of variable. So the true thing about parametric equation is nothing but a change of variable. Okay, it's just sometimes if you are smart, the right change of variable also give you some physical meanings. For example, sometimes the change of variable actually tells you an angle. Sometimes it tells you velocity, but it really depends on how lucky you are. So all the tricks we did before, we actually are doing parametric equation already. We just didn't write down both of them. We just did one of them. Okay, that's basically the idea. Okay, so we were talking about integrals. We were talking about area under a curve. We talked about volume. two more things, arc length and surface area. You do know every time I mention these two, I always mention them together because the formula is, the first one is going to be dl from A to B, that's arc length. And the surface area is always 2 pi r dl, right? So basically this dl formula is containing both of them. That's why I put them all together every single time. If you know how to do this, you basically know how to do this as long as you know what r is. So that's why. Now let's think about parametric equations. Okay, let's think about it. Remember, this time, let me write down what we had before. Before, what we had is a equals, if we take dx, equals this. I have a better way of presenting this. Before, what we have is this. Okay. But that requires y equals fx, right? Then you can take the derivative. But now what we have is, we don't have that. We have this. X is a function of t, and y is a function of t, another function of t. Okay, but we still want to imitate what you have here for this formula. Okay, now let's think about it. What do you want? The final formula definitely has to be dt, right? In this way, it has to be dt. Second, it should be exactly the same as this, otherwise you should have the same formula, right? So how do you get this formula from the beginning? Or how did you get dx? Why don't you just do dy? Then we start to realize, okay, if you really need to think about where this comes from, we have this dy over dx. This is the arc length. So it comes from the square root of dx squared plus dy squared. And then how did you get dx again? That's when I factor out a dx. And then this one is going to have a dx squared. This one is going to have a dy over dx squared. Okay. But now if we actually go back to this thing, now instead of factoring out a dx, you just factor out a dt. That's what you want, right? That's great. But that creates trouble, because that will give you dx squared plus dy squared. Before you have a dx squared here, when you factor out dx, and then the first one become 1, the second one become dy over dx, which totally makes sense. But this time, you just don't have this anymore. You have dt squared. That's it. That's the formula. I'm going to put the starting and ending point, alpha and beta. It may look tricky, but you do have the starting and ending point with t. You have dt. You have a formula like that, which come from exactly the same formula, so it's going to be working. It's just the thing in the middle of the, inside the square root feels tricky. Okay? But what is it exactly? It's actually dx over dt squared plus dy over dt squared. And that's it. What is dx over dt? Well, dx over dt is nothing but to take the x derivative with respect to x. What is dy over dt? That is nothing but dy over dt with respect to x. Okay, so that is going to be your arc length formula. Beautiful. Exactly the same idea. Instead of taking dx out, we take dt. But from here, you can see I write down the formula. This is for the formula of arc length, and this is for the formula of the surface area. It's basically nothing but the arc length plus a 2 pi r. Okay, so that's exactly as what we did before. But now, let's try to do some examples. And when we do examples of parametric, we always go with either easy ones, which you can see, or we can go with the cycloid, because the cycloid can only be done in parametric form. So let's go with the cycloid. Okay, so let's say we have a cycloid. We want to find the arc length. Again, I take r to be 1, so theta minus sine theta. Y equals 1 minus cosine theta. But you can try it with r and see how the arc length is going to change with r. My guess is going to be if you double r, you double the arc length. Okay, you double the r, you probably take 4 times bigger as the area. So that's normal. Again, let's draw the graph. Let's put for one complete cycle. Or you can put anything if you want. Okay. We wonder how long is this arc from here to here. Okay, this will be the circumference of the tire. So this one is definitely going to be longer than that. That's for sure, because it's the arc. Sounds good. So let's take the derivative, the arc length formula. Square root, depending on what you want. Okay, you want d theta, right? Then just put d theta from 0 to 2 pi. But if you put d theta, you better put dx over d theta squared plus dy over d theta squared. Just like if you put dx, you better put dx over dx, which give you 1. That's where the 1's come from. Now what is dx over d theta? That is going to be 1 minus cosine theta squared. dy over d theta is going to be 1 minus sine theta minus sine theta. Okay, that's going to be sine squared theta d theta. One minus 2 cosine theta plus cosine squared theta plus sine squared theta d theta. Okay. One good news about those kind of regular shapes is they always cancel out. Okay, because they're just such a nice form. Do you realize there is something you can cancel out with sine squared plus cosine squared? You can easily get 1. This 1 go with the 1, so you have 2 minus 2 cosine theta. Before you panic, this looks really difficult, right? Before you panic, just keep in mind, have faith. I don't know if that's the right word, but do have faith, right? It's a nice shape. It's related to circle. So, what is 1 minus cosine theta? And remember, you want a formula to transfer this one into a perfect square. So if you take the square root, it's gone. That's all the hint you have. And hopefully you can reflect. If you don't, pause. Take some time to reflect. I'm just going to try to save some time here. But really, you know this, okay? 1 minus cosine theta, that is the half angle formula. Do you remember which one? Right, so sine squared theta is going to be 1 minus cosine theta. But you need a double angle formula, so I'm going to put the thing here to be sine squared. Oh, 2 sine squared half angle formula d theta. Take some time to reflect that. But there's no shortcut. You just have to know the formula. Now if we take the square root, we have this one. We do have a plus minus choice, but your theta is from 0 to 2 pi. Your theta over 2 is from 0 to pi. Now what about sine? An angle between 0 and pi, it's always positive. So we don't have to worry about anything. D theta, this gives you 2 cosine theta over 2 times another 2 by chain rule, negative 2 pi 0, which give you, if you plug in 2 pi, that's cosine pi, 1, it's 4 minus negative 4, which is 8. Huh, it comes from a circle. This is 2 pi, which is 6.28 something for the horizontal one, and this one is exactly 8. Remember, this is actually what we said before. That is actually the fastest way. Not the fastest. This one takes the shortest time to roll from here all the way to the bottom. So that's actually the best distance you're designing for. So if you're thinking about designing I won't say an arc, more designing a skateboarding field. If you care about time, to minimizing time, this is the way you're gonna go. Okay, so the answer is 8. Beautiful. Okay, that's how do we do it. So this is just one formula. Once you have that, just plug in pick the right variable, then the right ending and starting point. In this case, we use theta. Once you have that, theta is basically will be the one you divide here and here. But once you have that, since your x and y are already in terms of theta, you know how to take the derivative. You just do it for twice. Very easy. And then for number 7, I'm just going to wrap things up. There's really nothing much to talk about here. So let's just use this one to find the surface area. Of a unit sphere. Okay. Volume of revolution, surface area by revolution, right? So we better just take this one. Now think about the formula from -1 to 1, 2 pi r dl, if you use dx before, and your r is definitely going to be y. So 2 pi y square root dx over dt square plus dy over dt square, because I chose to do dt. And because of that, I go from pi to 0. And because I did that, my y is going to be replaced by sine t. That's what we mean by using parametric. Then from pi to 0, 2 pi sine t dx over dt, that is sine squared t. There's a negative, I just chose to ignore it. Cosine squared t. Isn't that beautiful? Using parametric equation, then the arc length of the circle is the best thing which can happen. Okay, pi over 0, 2 pi sine t, and the 1 and the dt, which is 2 pi negative cosine. I'm just going to go with cosine, but then switch the starting and ending. Hold on, something is wrong. Perhaps I don't do it, but what did I do wrong? 2 pi sine t, cosine t was a negative, but then you plug in 0 and pi. Somehow I got negative 4 pi, and the answer should be positive 4 pi. Somewhere I screw up. Hmm. 2 pi r dl. Your r is 1. Oh, yeah, that's the reason. How do I say this? The answer is negative 4 pi. But then we're going to take the absolute value. and then we have 4 pi because we cannot have negative area. Okay. However, when you start to talk about things in 3 dimension, you will actually start to see we do have a negative area and a positive area, and it has everything to do with the orientation of your curve. Let me try to explain what's going on here. So consider a circle. The circle was formed in this way, starting from here, going all the way and back. Consider another circle, which is formed in this way. Go all the way back, and from here we can see this have the same area, right? Same area from geometry, but they have different orientations. But if you just imagine what's going to happen, if you do things in this way, you try to integrate your theta in this way. I'm just going to call it theta. And if you try to integrate your theta in this way, you are definitely going to have one positive and one negative. Okay? So in 3 dimension, when you start to talk about areas, even though the area will never be positive, negative, but you do have a negative area, but the negative there simply means the orientations are different. So for things like this, you need to be a little bit more careful. That is, when you do it, you probably need to take the absolute value when you finish, if you end up with having a negative number. Okay. Yes, because for your circle, you're going this way, right? But technically, if you take from the left to the right, your t has to go this way. So you actually reverted the orientation. But that is not something I want to go over in detail right now. Okay, that's it. So let's review what we had. We have how to take the derivative, basically just take the ratio. How to take the integral in the following 4 applications. For areas under the curve and the volume, you basically set up everything as you did before in x and y. When you finish, you just plug in x equals ft and y equals ft. Take the derivative if necessary, and then you're all set. For arc length and surface area, it's not that straightforward. You probably need to memorize this formula. But again, this formula really is nothing if you remember things at this level. That is, all dl come from this, which is the Pythagorean Theorem for infinitesimal small triangles. So then, no matter you want to do dx, no matter you want to do dy, no matter you want to do d theta, dt, whatever, you just divide by the same simple thing using algebra. For example, for d theta, you basically just need to match it with a d theta square on the bottom. But then you have dx square plus dy square. That gives you 2 derivatives. Okay, divided by d theta square. The concepts are really easy. You may not be familiar with it right now, so I think the best way to do this is just to do tons of examples until you become confident. Okay, there's no shortcut for doing things like this because it's a new concept. But the good thing is you can always trust your algebra. Whether you understand the thing thoroughly or not, you can always trust your algebra. Even though sometimes you're not sure. This is actually very common in mathematics. That is, when you are trying to do something complicated, you really don't know what that thing is going to tell you. So what you do is you just follow your algebra and make sure your algebra or your technical skills are right. Then whatever the final answer looks like, that will be the right answer. Once you are confident that you got the right answer, even though you have no idea what the right answer represents, then you can start to actually have some ideas about, yeah, since the final answer looked like this way, that must be telling something. And then that's where the new idea comes from. That is, I already know this one, even though it looks strange, but I know it's correct because I trust my algebra, then this strange thing should tell me some new insight. Okay, so try to get familiar with that. Sometimes even if you don't understand something, it will take time, but you can start to approach it by just doing repetitive exercises. Once you're confident with your computation, you always get the right answer. I think by that moment, you will start to build the connections.